Hello dears, this video is the first video in a list of videos I'm going to record, hopefully to help students who do not speak Arabic to understand the course of electricity and magnetism. In the first part of this course, we deal with charges at rest, or what is called electrostatic. So the charges we are dealing with are charges which is not moving. They are at rest. So we call this part of the course as electrostatic. So let's discuss four properties of charges. The first property is a well-known property that we have two types of charge. You already know this from chemistry class, that the atom consists of a nucleus where tiny particles called proton exists. The proton is positively charged tiny particles. Here also there are electrons orbiting the nucleus. The electrons are tiny particles which is negatively charged. So we have two types of charges, positive like protons and negative like electrons. The unit of the charge is C, Coulomb. C is abbreviation for Coulomb. We use the letter C to represent the unit of the charge. The values of the charge of the proton and the value of the charge of the electron are equal in magnitude. We use the letter E to represent the charge of the electron of the proton, and E equals 1.6 times 10 to the power negative 19 Coulomb. We can see in this table that the electron has a negative charge, negative 1.6, and the proton has a positive charge, 1.6. They are equal in magnitude with opposite signs. Here is another tiny particle called neutron, exists in the nucleus, but it is uncharged particle. So its charge is 0, and the atom all in all is neutral. Neutral means has no total charge. The total charge is 0 because the number of protons equal to the number of electrons. The second property of electric charges is well known also, that if you have two similar charges in sign, they repel each other. If you have a positive charge and a positive charge here, they are going to repel each other. They are going to move away from each other. And if you have two opposite charges in sign, one is positive and the second is negative, they are going to be attracted to each other. They are moving to get closer to each other. Let's discuss what is meant by charged object. The charged object can be understood by the process. If you have a piece of cloth and you rub this plastic rod, the rod and the cloth, initially both of them are uncharged, but the rubbing makes some electrons to move from the rod, okay, to the piece of the cloth. So this process ended up by having negatively charged piece of cloth and positively charged rods, because some electrons have moved from the rod to the cloth. So this piece of cloth now have excess electrons, and this is why we tell this piece has negative charge. The excessive charge on it is negative, and the excessive charge on the rod is positive. So the charging process is essentially a transfer of electrons from object to another, and we can tell that the charge is conserved. Conservation of a charge means it can't be created nor destroyed. We do the charging process by just transferring some electrons from object to another. So now the fourth property is about the magnitude of the charge. It tells us that the charge is quantized, which means it takes fixed value. How can we understand this property? We can understand this through the charging process. We said that the charging process is just transfer of electrons. So if one electron has been transferred to the piece of cloth, so Q should be E, one electron, a charge of one electron. If 2 electrons have been moved or transferred, so Q will be 2e. If 3 electrons, Q will be 3e, and so on. You will observe here that Q takes integer value times e. We can't tell that 2.5 electron is transferred from the rod to the piece of closure. This doesn't make sense. So Q should be written as NE, and N is integer to represent that whole number of electrons should be moved from object to another. Now, we have finished with the 4 properties of electric charge, and we are going to address the first law. The first law in the electrostatic part is called Coulomb's law. Coulomb's calculates the electrostatic force or the electric force between 2-point charges. We are not allowed to use Coulomb's law unless we are dealing with point charges. So what is point charges? The point charges are charges which is localized in very small, tiny points, and we describe it as point charge. So if we have a tiny particle here with diameter d and a tiny particle here with diameter d, such that the distance between these 2 particles are very big, greater than the dimensions of the particle, we can consider these particles as point charges. So these 2 particles will be attracted to each other or will repel each other according to the signs of the charges, as we have mentioned. So we need to calculate the electrostatic force as a vector. We need to know how to get the magnitude and how to get the direction. So let's start with the direction. We know that if we have 2 positive charges, they will repel each other, and if we have positive and negative charges, they will attract each other. The main point here is to take care that the line of action of this force is the line connecting these 2 charges. So attraction and repulsion occurs at this line. I have to connect the 2 charges, and as long as these 2 charges has the same signs, so repulsive force will exist, and the force acting on Q1 due to the presence of Q2 will be called F1. It will be to the left this way, and the force acting on Q2 due to the presence of Q1 will be called F2 to the right to represent the repulsion. And here we will have repulsion to negative charges. If we are talking about attraction, we have a positive charge and a negative charge. The attraction, we just reverse the direction of F1 and F2. If we have 2 charges like here, we have to connect the 2 charges as we already mentioned, and the repulsive force will be on this line. So I'm going to draw the force acting on Q1 in this direction down, F1, and I will call it F1, and the force acting on Q2 due to the presence of Q1 will be called F2, and it will be upward to represent the repulsive force. The force should be written in vector notation. Vector notation. We write dash under the symbol to represent that we are talking about vector. So such force which is inclined, we have to represent it with respect to the horizontal axis, which is x, and we know that the unit vector in this direction is I, and the vertical axis, which is y, and the unit vector in this direction is called g. So we have to make resolution for this force if we know the angle theta. Okay, so we will have 2 components, the horizontal components of the force, the one component which is beside the angle, adjacent to the angle, it will be F2 cosine theta, and the vertical component can be drawn here, or I'm going to draw it here. The vertical component, which is opposite to the angle, will be sine, so the vertical component will be F2 sine theta. So to write these 2 components, the horizontal and the vertical one, we are going to write it this way. 2 cosine theta, this is a horizontal component. If it is to the right, it is with I, it will be positive I direction, and the vertical component will be with J or opposite to J. Here is the component we have is with J, it is upward, so I'm going to write it positive, phi2 sine theta in the J direction. This is how to resolve the force and write two components. This component is the horizontal one, we can call it Fx, and this component is the vertical component, we call it Fy. And now we have completed how to write the force as a vector. Now we can go ahead to know what is the magnitude of F1 or the magnitude of F2. I assume that I have two charges, Q1 and Q2, so the force acting on Q1 is F1 and the force acting on Q2 will be F2. The Coulomb's law tells us that the magnitude of F1 is equal to the magnitude of F2. So they are equal in magnitude. They have difference or opposite directions, but the magnitude is the same. If we have 2 Newton acting on Q1, we have 2 Newton force acting on Q2 as well. And if we have 5 Newton here, we have 5 Newton here. So the magnitude is the same. The difference will be only that this one to the right will be plus I direction with the positive I direction, and this one to the left will be in the negative I direction. So how can we calculate this magnitude and take care that the magnitude is always positive? I'm going to calculate 2 Newton, always positive value. Magnitude is always positive. So when I am going to calculate the magnitude, I'm going to ignore the signs of the charge. Okay, I'm not taking any signs. I'm going to calculate positive magnitude all the time. So the magnitude of the first force, as we just tell, that equal to the magnitude of the second force, both of them equal to Ke, and Ke is constant. It is called Coulomb's constant. This constant is equal to 9 times 10 to the power 9 Newton meter square per Coulomb square. And here is the two charges, Q1 and Q2. We are going to substitute by Coulomb. Charge is measured in Coulomb. And here is the distance between the two charges as they are getting away from each other. The distance increase, the force should decrease, and the distance in should be substituted by a meter. So this is a constant is called Coulomb constant, is related to another constant, Ke equal 1 over 4 pi epsilon naught. This constant is pronounced as epsilon naught. Epsilon naught is the permittivity of free space, and it is another constant. You don't need to memorize this constant. They will be given to you in the exam. Okay, now we know how to calculate the magnitude of the force and how to know the direction of the force. But take care that Coulomb deal with 2 point charges only. So what are we going to do if we are dealing with more than 2 point charges? We have here a group of point charges, okay, and we are still dealing with point charges. I'm going to deal with this question as if it is required to find the electric force on Q capital. Okay, so the Q capital is here, the yellow one. And besides this charge, there is 3 charges, Q1, Q2, Q3. I have many charges beside this charge. So I'm going to use Coulomb's law to calculate the effect of Q1 on this big Q, and the effect of Q2 on this big Q, and the effect of Q3 on this yellow Q, and just then add all forces to get the total force acting on Q capital. Okay. So we are going to consider the effect of Q1 only on Q capital. I'm going to assume that all these charges are positive, okay, and this one yellow is positive too. So I'm going to connect the line. The line is drawn right here between Q1 and the Q capital. And then you are thinking of what is the electric force? What is the force on Q capital? How Q capital is going to move? We have 2 positive charges. There is a repulsion. The repulsive force makes this Q to move upward in this direction. So we are going to draw the force line just like that. F1 is the force acting on Q capital due to the presence of Q small 1. Okay. Now we want to draw the force acting on Q capital due to the presence of Q2. We are going to make the same procedure. I'm going to connect this charge with Q capital and then draw the force from here. I'm thinking of what is the force acting on this, how this charge is going to move. So I'm going to extend the line. It's going to be repelled by Q2. So the force here will be F2. Till now, we have two forces acting in Q capital. One due to Q1, and the second is due to the presence of Q2. The third charge, Q3, we are going to do the same thing. There is a line connecting the two charges, and we are going to do the force acting on Q capital with repulsive force, and it will be like this. Let's assume that the charge Q3 is negative. How can we deal with Q3 if Q3 is negative? Simply, this force will not be drawn in this direction. It will be attracted. The yellow charge will be attracted to the green charge. So I will just draw the attractive force in this direction. So this is F3 in case of this charge is negative. To get the total force acting on the big capital charge Q, we just need to add the three forces, F1, F2, F3. Just take care, we are going to add them as vectors. You have to make resolution for each force and then add the horizontal components to each other and add the vertical components with each other to end up with something like that. The total force on Q capital will be equal something like times I in the I direction plus something here in the J direction, and this thing is the horizontal components which we call Fx, and this thing will be the vertical component is Fy. Okay, how can we calculate F1? F1 is the force between the Q capital and Q1. This can be calculated by Coulomb's law. F1 is known, Ke. We are going to multiply the two charges times each other and forget about the signs, divided by the distance between them, R1 squared. The same way can be done to calculate F2 as a magnitude. F2 as a magnitude, not vector. I'm not going to put dash here. I am just calculating the magnitude of F1. The magnitude of F2 will be Ke Q. This force exists between the big Q capital and the red Q2. So I'm going to multiply Q times Q2 and divide by the distance squared, and so on. I can calculate F3 the same way. I can go to calculate F3, Ke Q times Q3 without signs. I'm going to calculate without signs. These magnitudes always positive, divided by the distance squared, and you can get this, how many newtons. You will know how many newtons here. I don't know how many newtons here. Okay, then you have to make resolution to add these forces together. This is what we are going to do in the next example. Okay, this is the first example to solve. I assume that I have 3 pointed charges, Q1, Q2, and Q3, and here is the signs of the charges. This is positive, and of Q2, the charge of Q2 is negative. We have distance here. I assume this distance is 3 meters, and this length is 4 meters. Okay. Now, what is the required? The required is the resultant force exerted on Q3. This is our big Q, okay? And I'm going to focus on this charge. How this charge is going to move due to the presence of Q1 and Q2. The two charges exist beside Q3. So, to take the effect of Q1, I'm going to connect the line, okay, between Q1 and Q3, and then think of drawing the force acting on Q3 due to the presence of Q1. Both charges are positive, so the repulsive force will be in this direction. This force is F1, and I can calculate the magnitude of F1 by using the Coulomb's law. The magnitude of F1 will be equal KE. I'm going to multiply the two charges together, the magnitude Q1 times Q3, divided by the distance, and I need this dash dot distance here. Here is 3 meters and here is 4 meters. This is a right angle triangle, so I have this distance 5 meters. We're going to divide here by 5 squared. This is the magnitude. I can calculate the magnitude this way. KE is 9 times 10 to the power 9. The charge should be substituted by Coulomb, but here we have microcoulomb. The micro means you have to multiply by 10 to the power negative 6. Okay, so the charge Q1 is 5 times 10 to the power negative 6, and both the charges are equal. Q1 is equal to Q3, so I'm going to write squared here, divided by 5 squared. Here is how we are going to calculate the magnitude of F1. So the force acting on Q3 due to the presence of this charge, -1, will attract Q3. So I'm going to draw the force acting on Q3 in this direction. This force, I'm going to call it F. Magnitude, okay, can be calculated using Coulomb's law. KE, we are going to multiply Q2 times Q3 and divide by the distance between them, which is 4 squared. Now, to complete this substitution, okay, we have 9 times 10 to the power 9. One of the charges is 5, and the other is -2. Remember not to include the sign. I take the effect of the sign already by drawing this red arrow. It is attractive force, okay? Don't include the sign again. 2 times 10 to the power -6. This is the two charges divided by the distance between them, which is 4 to the power 2. Now you can't add these two magnitudes because we have vectors here. We have to make resolution for the force. So if we know this angle, okay, the angle here is theta, and we know this length as 3 meters and this length as 4 meters. The angle theta here will be actually this angle, the same corresponding angle, two corresponding angles. So this vector should be resolved into two components. The horizontal component, which we just explained earlier, which will be F1 cosine theta. The adjacent to the angle will be the cosine, and this one will be sine F1 sine theta. Sorry, theta, not theta 1. We have only one angle, theta, not theta 1. Okay. Do we know sine theta and cosine theta? Yeah, from this triangle. This is a right angle triangle. Sine theta and cosine theta is already known. Sine theta equals 3 by 5. And cosine theta is known, 4 divided 5. Okay, we don't have a problem with this. And what is left is to write the total force as vector. You look at the components. Okay, forget about this one. We already resolved this force into two components. So we have this component to the right. I am going to write it positive. We have F1 cosine theta in positive. And F2 here is negative because it is to the left in the opposite direction to the eye. So I'm going to write it -2. So these are the horizontal components. Write the horizontal component either positive or negative according to the drawing. If it is to the right, positive. If it is to the left, negative. And all the horizontal components is in the eye direction. Then consider the vertical components. We have only here one vertical component, which is F1 sine theta plus F1 sine theta. So now I have just finished this question. Here is the vector form of the total force after we do the result and summing up the forces as vectors. Let's move to example 2. We have 2 point charges. Q1 equals 32 microcoulomb and Q2 equal 2 microcoulomb. The two charges is here. This is 32 microcoulomb, and here is the 2 microcoulomb. Then it is mentioned in the question, or given, that the force on a third charge, this is the third charge, the yellow one is negative. These two charges are positive, and I know it is positive because the value here is positive. If the value here is negative, I would know that it is negative. If the value is positive, so the charge is positive. And here is Q3 is drawn negative charge. Here is the symbol negative in the yellow one. It is given that the force on Q3 is 0. Find the distance x. Okay, the distance here between the two charges is 2 meters. If this distance between Q2 and Q3 is 2x, so we left with 2 minus x here. The distance left here is 2 minus x. Now the force on Q3 is 0. We know that the force on Q3 is the force due to two charges beside it. One force due to the Q1 and the second due to Q2. The force due to Q1 will be attractive force, so I am going to draw the force from Q3. It will be attracted to this blue charge, as this is the force F1. So the magnitude of F1 will be KE. This is the force between Q1 and Q3 divided by the distance between them, 2 minus x squared. And the other force acting on Q3 will be due to the presence of this red charge. So it will attract the negative one. There is the force F2. So the force F2 will be KE. Let's multiply the two charges together, Q2 times Q3, divided by the distance between these two charges, which is x divided by x squared. Now, to use what is given is that the force on the charge equals 0. We have two charges acting on this charge. The total force to be 0. We have two requirements. The two forces should be opposite in direction, and this is already seen from the drawing we have. The two forces already opposite directions, and they should be equal in magnitude to give total force of 0. So I'm going to tell that the magnitude F1 equal to the magnitude F2. If the two forces are equal, we can simply cancel KE with KE. We can cancel Q3 here from Q3 here. We end up with Q1 divided by 2 minus x squared equal Q2 divided by x squared. You can solve to get the value of x. Let's collect the terms with x in one side. Okay, we will have x squared with this here divided by 2 minus x squared equal, and we get Q1 in the denominator. Okay, we can substitute here. We have Q2 equals 2. We have Q1 equals 32. This will give 1 over 16. Then we have square here and square here. It's better to get rid of these squares. So we will get x divided 2 minus x. I'm taking the square root to the left side and the square root of the right hand side. So the square root of the right hand side will give 1 by 4. Okay. And then you can multiply, cross multiply, and get x. You will find that the value of x can be get very easy. This is the second example we have. Thank you. Good luck. Best wishes.